Is the recording on already? I'm not sure. Okay. Yeah, I think the recording has started. Okay. Yeah. So as I was saying, when we hook up the capacitor to a voltage source like this, just a battery, they will accumulate charges on the plates, and then because there's a charge difference, what will they do? They will produce an electric field. So this electric field stores energy like that. So when I want to use this energy, I could just remove this battery, and then let's say I hook it up to a light bulb, right? The potential difference is still there, right? This is plus, this is minus. So when I hook it up to the light bulb, then the energy from the electric field will go through and then make this light bulb shine. So essentially, that's the practical idea of what a capacitor is. It's an energy storing device. Uh, it works in a similar fashion for inductors. So inductors is still an energy storing device. What will it look? What will it look like? It will look like a coil of wire, right? It's a coil of wire. I think we call this a solenoid, right? I think you remember this is called a solenoid. So it's a coil of wire. I put it with a battery. I hook it up to a battery, and what will happen when the current passes through? Now, I think you recall from physics, current a current carrying wire produces a magnetic field around it, right? So for a solenoid, it will look like a bar magnet. It will start creating a magnetic field like this. And yes, this magnetic field stores energy. So I can remove this battery. Let's say I put a light bulb again, and this will give it energy to the light bulb. That's the very quick explanation of how these store energy. Okay, so the governing equation that you have to remember for capacitors is this. Okay, one of them is the formula for capacitance, right? So C equals to Q over V. The amount of charge you can so-called store between the two plates per unit of potential difference. And if you differentiate this with respect to time, you will eventually get this. So I equals to C dV dt. You do some rearrangement and you'll get this. So I think this is an important formula. This one, we less frequently use it, but I'm not saying it doesn't exist. Yeah. So these are the two most important formulas. That's for capacitor. Now, what about an inductor? Inductor, the governing equation is this. We will use this one. So instead of I, this will become V. So V equals to L, which is the inductance, di dt. Okay? So this is the governing equation for inductors. This one is inductor. And this is for capacitor. So you should remember this. Okay, there's another formula related to the energy stored inside it, but I'll get to it later when I do this question. So right now, we already know what a capacitor is. We already know what an inductor is. Now, what is the meaning of DC steady state condition? Sounds very scary, right? But actually, it's a pretty simple idea. So let me share screen with you my GeoGebra. So for the time being, I'll just share my screen. Okay, so if you ever seen what the charging graph of a capacitor or inductor looks like, it will look something like this. Okay, now let me explain what is going on. What is going on is when you first have your capacitors, right? These are your two plates. Right now, let's say I put it next to a battery. Okay, this is a battery, and then I have a switch here. So let me just put a switch like that. So I haven't closed the switch yet, right? It means nothing goes through, means the current is not activated yet. But when I close the switch, this will not, okay, let me just rewind my story. Let's say this is 5 volts, okay? A 5 volts potential difference, positive, negative. When I close my switch, this will not immediately at time equals 0. The moment I close my switch, this will not straight away become 5 volts immediately. Okay, this doesn't happen. What happens is it will slowly rise up until 5 volts. And that's the graph that I'm going to show you here. So this graph, the x-axis is time, the amount of time that passed after I close the switch, and the y-axis is the potential difference across the capacitor. So what I'm talking about is this one, the potential difference across here. So the potential difference across here is the y-axis. The time is how long after I close the switch. Okay, so let's go back to the graph. Oops. Okay. So you see, the moment I close the switch, right, at time equals 0, the potential difference will rise. It will rise, it will rise like this. Okay, it increases, 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 and then you see, notice that the gradient is stooping down. Okay, so let me just take a picture of this again. Okay, let me just put it in my OneNote. So put it here. Yeah. So notice that the slope of this will decrease, right? Initially, it was really steep like this, and it gets gentler and gentler, gentler, going down. See, the value of the gradient is dropping and dropping and dropping. What does DC steady state mean? DC steady state means that after a very long time, nothing is really changing. Okay, changing with respect to time, to be more specific. Okay, steady state means unchanging. Okay, and a very simple way to say is unchanging. Now, what I mean, you see, at the start of it, right, the moment I close my switch, okay, this is the moment I close my switch. So the switch closes at time equals 0. At that very moment, you see, the voltage, the value of the potential difference across the plates increases noticeably, right? It increases, increases, increases. But after a long time, a long, long time after I close my switch, what will happen? So let's go back to the graph. See, after a really long time, the moment after I close my switch, right? Yeah, it will increase, but it will increase up to the 5 volts, right? Remember the battery was 5 volts in value. It will increase until, see, what happens? This graph almost becomes flat, right? Meaning to say, after a really long time, this graph, the potential difference across the two plates will reach 5. It will stay constant at 5. See, now it is unchanging, right? The value of the potential difference across the plates is unchanging. That means it has reached steady state. So steady state, DC steady state means after you leave the circuit to settle for a very long time, all the capacitors and inductors are considered fully charged. Okay, depending on the potential difference across them. Or for inductors, it is the current through them. Okay. So now that we know what steady state means, we have to know how to analyze, okay, how to do the circuit analysis, which is what this question is tackling on. So when, okay, the question will tell you, like for example, find the energy stored. Yeah, so find the energy stored in the capacitor and inductor at DC steady state. So when you see DC steady state, right? When you see the words DC steady state, it means DC steady. Okay, let me not write this here. So what happens to capacitors? What happens to inductors? Capacitors will become short circuits. So I'm gonna write here DC steady state. Okay, when they say DC steady state, it means after a very long time, what happens to the capacitors? They are just as though you open the circuit. So this is the terminals. So this is the terminal. And it's like I open the circuit, just like that. So capacitors, essentially, they get removed when you reach DC steady state. It's almost as though there's nothing there. What about inductors? So inductors will become, during DC steady state, they'll just become short circuits. Now, what does short circuit means? It just means I pretend that they're just connected by wires, right? Just like that. So you remember that when they say DC steady state, all the capacitors become open circuits, while all inductors become short circuits. Now, I don't know if this is a helpful trick to remember, but for me, I noticed this interesting observation. You see, remember I told you that these are just two plates, right? and then attached to some wires at the two ends. What I think is when I see DC steady state, how I conveniently remember these effects is like this. Imagine you are here, and then what happens when you pull these two apart? You pull this way and you pull this way. Then it becomes a open circuit, right? There's a gap in between the capacitors. Yeah, between the two plates, right? You just pull them apart and it become an open circuit because there's a gap now. There's a huge gap. Initially, the gap was close enough for the electric field to uh, go across the gap, but now when you pull it apart, it's an open circuit. Then now pretend that you are for inductors is the same thing. Imagine you're here, and then you hold on to the two ends, the two terminals of the inductor, and then you pull them apart. What happens? See, this was a coil of wire, right? When you hold the two ends of the coil and you pull it apart, it just becomes a straight wire, right? This has no logic or whatsoever to it. It's just a convenient way to remember what happens at DC steady state. So for capacitors and inductors, the effect of DC steady state, right, is just like I pull them apart. So I pull the capaciting plates apart, they become like a huge gap, which is a open circuit. For the inductor, when I pull the coil straight, it becomes a wire. So it's just a convenient way to remember. It's nothing logical to it. Okay. So with that being said, let's go back to our question. I think I'm gonna move it down here. So bring it down. Okay. So what do? We use whatever I said. So all capacitors you see will be open circuits. All the inductors you see will become straight wires. Okay. So let's go ahead and find out where our capacitors are. So here's a capacitor, here's a capacitor, here's a capacitor. So what will happen? They all become open circuits. So this branch will be gone. Okay. When I remove this capacitor, this branch is open, right? So effectively, there's no current through this whole branch at all. If there's no current in that whole branch at all, I just might as well remove the whole thing, including the resistor, right? You see, there's a resistor down here. Because there's no current going through it, so I might as well remove the whole branch. So I remove the whole branch. Then here's our capacitor. I also open circuit it, just remove it. Okay. Then here's our inductor. What I do? Turn it into a short circuit. So just turn it into a straight line. So just short it like that. So now what you're supposed to do after you identify what to short and what to open circuit, you just redraw the circuit. Okay, don't be a lazy bum. Just redraw the circuit as you have already simplified it using the DC steady state. You see, that's what the hint is trying to say. It becomes extremely simplified. Okay, I'll show you why is it extremely simplified. So bear with me. So I'm gonna recopy this. So it will look like this. Right? I'm just gonna copy this 6 volts. So this is the terminal of the capacitor, but the capacitor is gone. Oh, sorry. So this is the 2 ohm resistor. It still exists. This is the terminal of the capacitor. And then this is the 4 ohm resistor. Right? I didn't remove it. I just leave it. Okay. The capacitor up here is gone, so no need to do anything. Then let me just move more to this side. So see, the inductor becomes a straight wire, right? So just draw a straight wire. This is the other terminal. Then this branch is gone. Wait, let me remove this meeting sign. So this terminal is like that. I just ignore it. Okay, don't include the branch. And then this is the 8 ohm resistor. 8 ohms. And then just connect it back. Right? You see, it becomes so much simpler. And what do we do? Again, mesh current analysis, right? You're always going to be using mesh current analysis, no voltage method, so on and so on. But in this case, I will use mesh current analysis. So let us just do that. This is mesh A. This is mesh B. So let us do our favorite thing, KVL. So move down here. Okay. So okay. So let's start from do KVL at A. So KVL at A. We start from the red dot. We go up. So this is voltage gain because we're going from negative to positive terminal. Negative to positive is voltage gain. So positive 6. Then after going through here, we go through the resistor. So resistor is negative because of voltage drop. Minus IA times R. Then we go through the 4 ohm resistor. See, the 4 ohm is in the middle branch, so it is IA minus IB. So minus IA minus IB multiplied by 4 ohms. Okay, multiplied by 4 ohms. And then after we go through that, we return back to our dot so we can equate it to 0. So if you expand and simplify this, you should get minus 6IA plus 4IB equals to negative 6. And this is our first equation. Okay. Next, we look at KVL at B. So again, mesh current analysis, KVL at B. So we start from anywhere we want. Let's start from here. So let's go to here. So it is, minus, because it's a resistor, voltage drop, IB minus IA times 4 ohms. Then we go to the 8 ohms. Okay, so after we go to the 8 ohms, minus IB times 8. Then after the 8 ohms, there's nothing left. So we just return back to the original. So equals to 0. Then you expand and simplify this. You should get 4IA minus 12IB equals to 0. So this is our second equation. Yay, 2 equation, 2 unknown. Punch it in your calculator. Solve 1 and 2. You should get. So this is IA equals to 9 over 7 and IB equals to 3 over 7. So I'm just going to leave it as fraction to keep it accurate first. Let me see if Kyle is here. Is Kyle here? Oh, I want to tell Kyle about something similar. He texted me about this. I don't know if he gets it or not. Okay, never mind. Don't care. He didn't attend. It's his problem. Okay. Okay. So again, don't forget our mission here is to find the energy stored, right? So energy stored for capacitor, the formula is this. So E for capacitor is half CV squared. Kind of ridiculous, but it really reminds you of kinetic energy formula, right? Half mv squared. Okay, but that's irrelevant. Okay, it's just an analogy only. It's just a convenience for you to remember. So half CV squared. Actually, right, what I should specifically write is half delta V squared. Because you're not relying on a single voltage value to keep the energy. What you're relying on is a potential difference, right? The potential difference across the two plates. It's not like I say, okay, I use 5 volts here to store the energy. What I'm using is a potential difference across these two plates, delta V, to store energy in this capacitor, right? So it's actually, to be technically right, it's delta V that is storing the energy. So that's why I write delta V here and not just V. Okay. For inductors, it is half Li squared. You can see that they're quite similar in nature, right? Here is a constant, which is capacitance. Here is a constant, which is inductance. And here's potential difference, whereas here is current. So it's kind of similar in a sense, right? Anyways, so with that being said, let us find the energy stored in all the capacitors and inductors. Now, the question to ask is, after we remove the capacitors and inductors, right, we're going to put it back. We are going to put it back only to visualize what is the important information to find the energy. Now, let me explain what I mean. So remember this one? Remember this capacitor that we moved? I'm going to put it back for a while. Treat it as invisible, but just remember that it was there. Okay, so this is invisible. It's not actually there. So why I do that is, okay, just to allow you to visualize. So remember, for a capacitor, it is half C delta V squared, right? So the C we know, the C they told us is 2 farads, and we need to find the delta V. So that is why we did the mesh current analysis, because it helps us get the delta V. Now, how to find the delta V across this terminal? So the terminals that we're talking about is this and this, right? Because the capacitor is between here. So we need the potential difference across these two nodes to find the energy stored. So let us find that. So first things first, we need to identify a reference point. Meaning to say we need to put a ground. So put it anywhere you want. Let us just put it down here, right? At the bottom. Excuse me for a while. So when we, okay, let me just keep it that highlighted. When we know the bottom is ground, this whole thing is a node, okay? This whole thing is a node. Why? Because ask yourself, is there any devices within this node? No, right? So that means that whole thing is one single node voltage value. Tell me, what is the voltage value of the bottom node? Anyone tell me straight away? Put it in the chat. 0, right? Because it's connected to the ground. That's why I put the ground. So we know it's 0. So let me just highlight this. Whole thing is 0 because of the ground. Then, you see, let us start from the ground and let us walk through this voltage source. So after I pass through the voltage source, what is the voltage value of the corner up here? Anyone tell me? Say in the chat, 6, right? Because I start from ground, which is 0, then I had to go across a potential difference of 6, which will bring me 6 volts up here. So this one I will just label as 6 plus 6 volts. Okay. Then, you see, now the value I'm interested is this one, right? So let us use this formula. Delta V equals to V start minus Vn. Okay, so I'll show you why. Okay, yeah, so we just paste back the formula here. Delta V equals to V start minus Vn. So the delta V that I'm referring to is this one. Okay, between this node and this node, this is delta V. Okay, so you see the current is going this way to this, right? This way to this way, right? So it starts at 6, it ends at the one we want. So let us just call this VA. Okay, the value of this node, I'm gonna call it VA. So it starts at 6, it ends at A. So V start minus Vn means 6 minus VA. This is 6 minus VA. Now, how do I find the value of delta V? Delta V is equal to, remember, Ohm's law, I times R. In this case, the current going through this branch, is IA, right? IA is the one going through this branch. So actually, I should write IA. So IA is, we already found this now, is 9/7. So 9/7 times, the resistance is 2 ohms, equals to 6 minus VA. So if you find VA, you should get 3.43. Yeah, I should have left this in fraction, but I just calculated 3.43. Okay. So now we know that the value of VA is actually 3.43, right? Right? This node is 3.43. You see, the bottom green node, this one, has a value of 0, right? Because it's connected to ground. It's just 0. Up here, it is 3.43. So I know the potential difference, 3.43 minus 0 equals to 3.43. So the potential difference across this capacitor is 3.43. Understand? I'm going to repeat it again. See, we start with a reference point, right? I just connected to ground. We go up, we find this node. Why we find this node? So that we can find the value of this node using V start minus Vn, and then we use Ohm's law. Delta V equals to I times R. We combine that together, we can find VA, right? And then this node, which is 3.43, minus this node, which is 0. 3.43 minus 0 is 3.43. So now we know the potential difference across the capacitor is 3.43. So now we can finally find the energy. So energy is equal to half CV squared. Half times the capacitance is 3. Let me check. Oh, sorry, the capacitance is 2. So 2 times 3.43 squared. Ah, sorry, I didn't say. This is delta V, right? Sorry. It's 3.43. Then if you calculate it, you should get 11.76 joules, which is one of the answers, right? Yeah. So 11.76. So this is correct. Next, we want to find the other capacitors. So let us look. So another capacitor that we remove is this one up here, right? So let us find the potential difference across the capacitor. Because remember, for capacitor, the energy stored is half C delta V squared. So we need the delta V of it. So that means the potential difference across this node and this node. But let us go back to our diagram. And that is why I say, just put it back to the diagram where you remove all these devices, where you simplified it already, the steady state one. So I'm going to clean this one up. Just remove this. Clean this, clean this. Okay. So remember, we put the capacitor, let me check, here. Okay, let me just relabel this out, sorry. This one is 3.43. Okay, we actually put the capacitor up here, correct? Now, look at this. We want to find the potential difference across the two nodes here and here, right? But this is funny. Why I say it is funny? Because look, agree with me that this is a single node, correct? Ask yourself, why? Because do you check, is there any device? No devices across here, right? No device means that whole thing is a node. If it is a node, that means it is only one single voltage value. There's no potential drop, there's no potential change across this whole node. So what does that mean? There's no potential drop in that node means the potential difference between this terminal and this terminal is 0, correct? Because, again, I'm going to repeat, this whole thing is a single node, no potential drop across it. That means delta V across this terminal, across this and this terminal is 0. That's why you plug in E equals to half C delta V squared. This is 0, right? That means the energy stored is 0. That's why there's a 0 here, right? Yeah, there's 0. So that's the end of that story. Now the other capacitor. So the last capacitor is over here. Let me just clean this again. So the capacitor we are interested in is this one, right? So let's just put that back. So here, it's over here, and there was a resistor, but this resistor honestly doesn't matter. Okay, the point I'm trying to make is we need to find the voltage difference across this terminal and this terminal. Now the bottom terminal, again, we already know this value is 0, connected to ground. What about this one? Up here, you see, keep in mind that this is still an extension of up until here, right? The node can stretch all the way until here because, again, ask yourself, is there any device within this segment? No, right? No device, no device, no device. That means the potential difference across this whole segment is the same. And remember, see, we already identified the value is 3.43. Can? Okay, I hope this is clear to everyone. So you have to have a sharp eye on what is a node, right? If you didn't see that is a node, then you wouldn't recognize, oh, who contains which value of voltage. Okay, so this is 0, and I'm gonna keep coloring this so you know that this whole thing is actually still 3.43, which came from here. Okay, meaning to say, see, up here is 3.43. Down here is 0. The potential is still, the potential difference across the capacitor is 3.43. So E equals to half CV squared, half, I think this one is 3, right? 3 farads. Yes, 3 farads. So multiply by 3 farads times, the potential difference is 3.43 squared. So if you punch this into your calculator, you should get 17.6 joules, which is one of the answers, right? Yes, it's 17.65. Okay. Then lastly, we have our inductor. So inductor, remember, this time we're not looking for potential difference. In inductor, we're looking for current, the current going through the inductor. So let us go back to our steady state diagram. The steady state diagram shows that the inductor used to be where? The inductor used to be here. It used to be inside. Okay, let me just clean up my diagram. So the inductor used to be here. So that means we need to find the current through this strand of wire, right? Through this strand of wire. So what is the current through that strand of wire? It's just IB. Don't forget that this was the mesh current that belonged to IB. So the current going through this one, going through the inductor is IB. So we already solved IB, which is 3/7. So now just use E equals to half Li squared, half times L is what? So the value of L is, oh sorry, let's go up 2 henries. So multiply by 2 times 3/7 squared, you should get 0.18 joules, which is the right answer. Okay? Yeah, that. Oh, sorry. I mean, yeah, there's a 0.18 up there. So yeah, it's correct. Okay. I think that should be fine, right? So this is DC steady state. I'm gonna recap what's the main point of this. Whenever you see capacitor, change it to open circuit. Whenever you see inductor, change it to short circuit. You do the mesh current analysis, you find the values of, so if you want energy stored due to capacitor, use the formula half C delta V squared. Meaning to say, wherever you put your capacitor, you need to find the delta V. Then for inductance, you need to use half Li squared. So that means you need to find the current going through the inductor. Okay, so that's the TLDR of this. Now, the next topic we want to address is RMS and, wait, is it this one? Oh, sorry, capacitors. So again, I'm gonna recap the formula. Actually, there's no question related to inductors, which I don't understand why, but I think in tutorial 11.2, there's one related to inductors. So we'll get back to that when we reach there. So for capacitors, the governing formula is this. I is equal to C dV dt. And then for inductors, the governing equation is C equals to L di dt. So this one is capacitors. This one is inductors. So in this question, we are given the waveform of sorry, let me just read it out. If the waveform shown in the following figure is the voltage across a capacitor, okay, so that means the governing equation we are interested in is this one. Plotted with a function of time is this, with a peak voltage of 20 volts and a period of 40 microseconds. Okay, I hope you know that mu. This is the Greek letter mu. It stands for micro. Micro is what? Can anybody tell me what is the order of my micrometers? I mean microseconds. 10 to the power of what? -6. Yeah, thank you. So 10 to the power of -6. So micro is 10 to the power of -6. You have to be careful of this, because sometimes they give you millivolts, sometimes they give you milliamperes, sometimes they can even give you picofarads. I think, if I'm not mistaken, pico is 10 to the power of -12. Yeah, so be clear with your prefix. Yes, you have to memorize those prefixes if you haven't already. Okay, so keep that in mind. So wherever you see prefix, you have to change it back to normal. So we'll do that later. So what is this? This is nano. Nano is 10 to the power of what? Anyone tell me? -9. Thank you. So yeah, nano is 10 to the power of -9. Determine and plot the waveform for the current through the capacitor as a function of time. So again, the formula we are interested is I equals to C dV dt. Now, this is a voltage versus time graph, correct? And then in the formula, look at this. This term says dV dt. What part of the graph gives me dV dt? Can anybody tell me in the chat? dV dt is what part of the graph? The slope, right? Samuel says the slope. Correct. dV dt is the slope of the graph, meaning to say the gradient. Okay, if you all don't remember, it's the gradient. So how steep it slants. So with that being said, okay, so this one is the gradient of the V versus T graph, right? So here we're given the V versus T graph. So meaning to say, if we want to find the current through the capacitor, we need to find first the gradient of the graph, and then we multiply, don't forget to multiply by the capacitance. So multiply by the capacitance. That's something you cannot forget. So let us go ahead and do that. So let us focus on this single period first, the first period. The first period, how to find gradient. So gradient, go back to secondary school. The formula is m equals to y2. Okay, in this case, in this context, let's just replace m with dV dt. Is equal to y2 minus y1 over x2 minus x1. So meaning to say we need 2 points, right? So one point is this one. One point is the origin, correct? So this is 0, 0. Another point is up here. So t is 40 microseconds. V is 20 volts. So I is equal to let's just leave C first. C times, okay, actually let's just plug it in now. Straight away plug in the value. So C is 680 times 10 to the power of -9. Don't forget it's nano, so change it. Times the gradient of the graph. So the gradient, we could use our secondary school formula, which is y2 minus y1 over x2 minus x1. You should get y2 is 20 minus 0. Then y1, I mean x2 is 40 microseconds. Okay, don't forget microseconds means I change it to like that, minus 0. Okay, don't forget the prefixes. See, in this one I accounted for the nano, in this one I accounted for the micro. So when you do that, I didn't calculate it, but you should get 680 times 10 to the power. Oh, I calculated up here. So you should get 0.34 amperes. Sorry, I have my answer script here. This is 0.34 amperes. Now, let us go back and have a look at our VT graph. Why? Because now we need to identify the shape of the current time graph. Remember that the shape of dV dt will somewhat give us the shape of the current versus time graph. Okay? So here, I ask you this. This is a straight line. Right? Straight line means the gradient is constant. Right? The value of this gradient throughout this whole line doesn't change. It keeps being stuck at that gradient, right? So when you multiply it by the capacitance, it is always at 0.34 amperes. So the gradient throughout this line is constant, right? Meaning to say on the I versus T graph, the current versus time graph, it should look like a constant straight line, right? The gradient doesn't change in this period, so it must be a horizontal flat line like that. Okay, so this is the first period. And then this value is 0.34 amperes. When I go to this second section, again, it is the same slope. So straight line means it's a constant gradient. It is a constant value of 0.34 again. So essentially this is 2t, like that. Let me just make this better. So it's just simply like that. The constant straight horizontal line. Can everybody get this? So it's a straight line. Straight line means it's just a constant gradient. So constant gradient, the value doesn't change on the I versus t graph, right? So it's just a straight horizontal line. Determine and plot the waveform. Yeah, it's just like that. So you have to remember the governing equation, which is I equals to C dV dt, and then recall that dV dt on the voltage versus time graph means the gradient. That's why I calculate the gradient. Okay. Now let's just move on to RMS and mean. Let me check how many people are there. People, oh, only 8. Maybe I need to close shop my PTP. Should I close shop my PTP, guys? Should I resign early? No. Why? I don't get much not much support. Might as well close the PTP, right? It's a waste of my time, it's a waste of your time. Okay, just kidding. Let's just focus on this first before I resign. So find the ratio of the average and the RMS values of the waveform. So let's forget about circuits first. Let's just go back to primary school, because who doesn't love primary school? I give you 5 oranges. Let's say the oranges weigh, I don't know how much oranges weigh, 200 grams, 201 grams, 200 grams, 202 grams, 203 grams. Okay. Now, I ask you, calculate the mean of the weight of all these oranges. How would you find the mean of these oranges, the weight of the oranges, the mean weight of these oranges? Can anybody tell me? What must you do? How to find the mean weight of these oranges? Yes. Add the weights all together. So add this, add this, add this, add this, add this, and then divide by the number of oranges. So there are 5 oranges. I just divide by 5, right? So total, essentially, right, for mean is total divided by the number of values. So why am I addressing you this? Because I want it to be clear and intuitive for you to remember the formula for mean and RMS later. Now, let's go back. Okay, this is primary school. Now let's go back to university. In university, how do we do total for a function? We do total by doing integration. Okay, let me explain why. So this is just give a random function, something like that. So what we do is, we cut it up into little skinny rectangles, right? Very thin rectangles. We call them infinitesimally thin. Okay, it doesn't matter. Don't scare yourself. There are many thin rectangles, and just treat them like the oranges. So what do? You total them up. You total by using, if I want to find the mean of this, so mean is equal to, I total this up by using integration. F dx, right? All of these are the dx's. All these tiny little increments are the dx. So by doing integration, I sum them up. So that is the total over the number of values, right? The number of values, if I add all these dx's up, this dx, 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 and so on, da 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 da. If I add all this together, this will give me the, okay, in the case of a periodic function, right? For example, this one. This is a periodic function, correct? If I add, okay, if I focus on one period, just focus on this one, and then I slice it up into all the infinitesimals. If I add all these infinitesimal elements up, these all will give me one period, correct? The total of all these dx's, I add them together, will give me one period, correct? So if I want to find the mean value of one period, what I do is I integrate it over one period, right? So I forgot to put the boundaries from 0 to t. So this is one period. and then divided by t, right? Again, just go back to our idea of what mean is. Mean means total divided by number of values. I hope this is clear and how it's more intuitive to remember mean when you do circuits. So number of values. So you just integrate it over one period and you divide by the period. So let's go back up here. Now, what about RMS? RMS stands for root mean squared. Now, literally from the name of it, right? Root mean squared. You can tell what is the formula of RMS. Now, let me explain. So, first, root. So we need to draw a square root, correct? Then mean. Just now we already discussed. Mean is the total. So I integrate over one period. Rather, I should put t, right? Because we're dealing with time. So this is t. This is t. So total from one period divided by the period. Then what did they say? They say squared. Squared, right? So that means I need to square the function. Okay, I squared this function. You see this? This function inside, I squared it. So let me recap, right? How to remember the formula for root mean squared? Literally use the name of it. This is the root, right? Root. Then next is the mean. So we calculate the mean and then the square. So you square the function. Ken, I hope this is clear because you have no cheat sheet in 2009. So you have to remember the formula for root mean squared is using this root, and then you take the mean, and then you square the function inside. Can? Okay. So you have to remember this formula, right? Because I know in the PYPs, they don't show up much. RMS for some reason doesn't show up much in the PYPs, but surprise, surprise, it came up for my semester last semester. So yes, you have to remember these formulas. Don't neglect them. Okay, everything in the lectures is testable. So yeah. So first we need to find the average, then we need to find the RMS. So let's go ahead and find average first. Copy and paste. So let's find average. Average, again, the formula is, so mean is equals to, you total it over one period. So in this case, it's voltage. Then divide by the period. So you integrate over one period. Now, what part of the graph gives me integration? Can anybody tell me? This is basically AMATs all over again. Tell me in the chat. What part of the graph gives me? Yes, area. Thank you, Vishnu. So integration gives me area, right? So in this case, I don't need to do, any of those integration tricks. I just look at the area of the graph. Area here and the area here. Then I total them out, I find, and then I divide it by the period. So let us find the total area under the graph. So you see, this part of the graph is below the x-axis, right? Meaning it's negative. See, it's negative 9 volts. So this area is also negative, Yeah. So let me just specify. This thing is actually area divided by period. So area of, area of one period divided by the period. So this part is negative. Now, this is a rectangle, right? Rectangle, the area is given by length times breadth. So the length is 2, the breadth is 9. 2 times 9. What about this area? This area is positive. And then it is, what is this? Length times breadth. So it's 2 times 1. Oh, sorry. 2 times 1. So this value, you get negative 18. This value up here, you get positive 2. Now you total out the area. So when I do this, I will get negative 18 plus 2 divided by the period is 4, right? See, the period stretches from 0 all the way until 4. So divide by 4, you should get, so this is negative 16 divided by 4, you should get negative 4. Okay, so this is the mean. Next, we have to find the RMS. So again, RMS, how to find the formula? So RMS is given by, first, root, then mean. Then square, root mean squared. Okay, so square the function of voltage. Again, what does integration mean? Integration means I need to find the area. But the area of what graph right now? Not the area of this graph, It's not the area of this graph directly. It is the area of this graph, but squared. Oh, I don't know why is my thing going haywire. Okay, it's back to normal. Okay. Oh, sorry. So this one, now we are finding the area of square graph. Okay, emphasis on the square. What does that mean? Area of the square graph. What? Did someone open the mic?
Yeah. Can you hear me?
Yes.
Dixon, why didn't you find the area above the origin? Why do you only and below, like the whole square?
I didn't understand. What?
Uh,
Why didn't I find which area?
the top part of the first square and the bottom part of the second square.
You mean this one?
Yeah, correct.
I mean, look at it, Vishnu. Integration, right? Let's say, for example, integration, or let's say y equals to x squared. Isn't it the area? Okay, let's just say this is 1 and this is 1. If I integrate 0 to 1 x squared dx, isn't it the area under the graph? Area under the graph. Rather, it's area between the graph, the curve, and the horizontal axis. So let us go back to here. The graph is this line. See this black line? See this black line? See this black line? So the area between the area given by the integration is the one sandwiched between the horizontal axis and the curve, which is this one. And this is the curve up here and the horizontal axis. Correct, Vishnu? Do you get it now?
Also, is always just the horizontal x-axis and the graph. Is it the area between the x-axis and the graph?
Yeah, between the curve and the x-axis. I mean, like, for example, let me just show you another random function. So I'm just going to show you a random function. Let's say I integrate from a to b. So this is a, this is b. So this is the curve. So the area between the horizontal axis and the curve is this, isn't it? Right? So this one is integrate a to b f of x dx. Right? Let's say from here to, so let's call this c. So I integrate from c to a f of x dx. It will give me this one. So between the curve and the horizontal axis, correct? So if
Okay,
I
yeah,
go
I
back
get
up
it.
here,
Thanks.
yeah, okay, yeah. So emphasis again. I know Vishnu gets it now, but I hope I clarify something for everyone. So see, this black line that they draw, this squarish line that they draw, is the curve. If I integrate it, means I find the area between the curve and the horizontal axis. So this one, let me do red. So this one and this one. Okay. Now let us go back to RMS. So RMS. So remember RMS is this formula, right? But I squared the VT. I squared V of t. What does that mean? If we're doing integration of 0 to t of V squared t, I need to find the area of the squared graph. Area of the squared graph. What does that mean? Means for all the values I see here, I need to square it. So let me copy down this diagram. So let me make it clear. So what I'm gonna do is I'm gonna make a v squared t graph. Means every y value I see here, I will square it. So this thing, I will square it. This thing, I will square it. So 1 squared is 1. -9 squared is 81. Okay? Negative times negative becomes positive 81. Okay? So if I redraw this, it will become, so this is v squared right now. It will become like this. So this one shoot back up to 81. Okay, it's no longer negative anymore. Then this one will drop back down to 1. Okay? Then this is from 0 to 2 and then 2 to 4. Is everyone clear with this? This is really the crux of what it means by the integration of a v squared t graph. All the values that I see from here, see, from here to here, from 0 to 2 seconds, it is -9, right? So I square -9, I'll get 81. And then from 2 to 4 seconds, it is 1 volt. I square that, it becomes 1. So now I plot a v squared t graph. Now I want to find the integration of the v squared t graph over one period. So that means I just find the area under this graph, right? So the area in this rectangle, so let's just call this rectangle A, rectangle B. So the area of A is given by length times breadth, so length times breadth. So 81 times 2 is 162. Then for B, length times breadth is 2 times 1, which is 2. I add up this area, I will get 164, right? This is the value of my this 0 to 2, I mean, yeah, 0 to t integration of v squared t dt, right? This means the area under my v squared graph, on the area under my v squared graph. That's why I create a v squared graph, which is this one, and then I find the area under it. I total them up, I'll get 164. So let's just go back up. So now we know this value up here is 164. So this one becomes 164. And then the period is still 4, right? The period is still 4. It didn't change. So it's 4. Now, if I do this, I will get square root of 41. Now, the question asks me, determine the ratio between the average and the RMS. So that ratio will be given by ratio is equal to the average, which is the mean, divided by RMS. The mean we just now got was what? -4 divided by square root of 41. Now let's punch this into our calculator. -4 over root 41, we should get negative 0.62523 significant figures. And yes, this is indeed the answer. Yeah, negative 0.625. Up until here, does everybody get? Let me check the chat. Is everyone okay? Vishnu okay? Brian okay? Horan okay? Ain? Who's Muhammad? Oh, hi there. Everyone okay? This is quite a difficult question, I must admit. Okay, everyone give me a thumbs up. Yeah, so surprise, surprise. This is quite easy already because all of these are constant values. So all of them are just area of rectangles. Can they give you a slope? Yes, the answer is yes. Who got the slope? Me. I got the slope last semester. So what they gave me is a sawtooth wave, I think, like this. So what are you supposed to do? You're supposed to identify this is some equation, right? So this is like y equals to mx plus c. And what do? You have to integrate this. Yeah, and then for the RMS, you need to integrate this whole thing squared, something like that. Yeah, so I'm telling you from experience, yes, you don't neglect this. I know it doesn't show up much in PYPs, but surprise, surprise, it did for me. Okay? Okay, that's RMS and average. Now we have to move on to capacitors done, DC steady state done. I want to move on to phasors. Okay, so phasors, we begin a new chapter in our life, in our journey through circuits and engineering. I think this is quite a interesting chapter, if you ask me. So we used to be babies, right? Why do I say we are babies? Because we used to study everything in DC. DC is fine, right? Nothing is changing. The voltage is never fluctuating left and right. But in reality, most things are AC, right? You hook up your mains switch, everything is AC, correct? Because the way we generate power is always AC. That's why AC is a more widely applied form of current or fluctuation in current and voltage. So now we begin a new chapter of our life that is AC analysis. So have you all begun on phasors and impedance yet? Can you all tell me in the chat? Because I know in tutorial 6 there's already phasors. That's why I want to begin on it. Can anyone tell me, have you all started phasors yet? Yes, no? Is it part of this week? Yes, but DK what Domenico is talking about. I understand. I understand. Okay. So why phasors, right? Why does phasors exist? Let me tell you what is the reason it exists. So why phasors? And when we also talk about phasors, right, we also talk about impedance. So I might as well talk about that too. So why phasors and impedance exist? So if you want the funny reason, what the whole story that Professor Domenico was talking about in the lectures, right? He talked about something about ODE, time domain, blah 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 blah, right? It's just a long-winded way of saying engineers hate solving differential equations. And it's true. Have you ever taken MH1811? It is the second math course of engineers, MH1811. In the last chapter, right, you'll be solving thousands of bloody different types of differential equations. There are homogeneous differential equations, Bernoulli differential equations, second order, first order, exact differential equations. Many have their own special way of solving them, and there's so much hassle to deal with them. So yes, I'm not kidding when I say engineers hate solving differential equations. So it's literally no joke. It may sound funny, but it's really a practical reason. But here is the moral of the story, which I do not get why Professor Domenico did not raise as a problem of why we study phasors and impedance. The biggest and most serious revelation is this. Sorry, I should change it to some different color. We can use calculators to solve AC now. Yes, this is the most practical reason of why we use phasors and impedance to solve AC analysis. I'm serious. I'm dead serious. Because we change everything into complex number form. Right? Calculators, only powerful calculators like your laptop can solve differential equations. But of course, you're not going to bring your laptop to the exam hall, correct? What you can do is bring your calculator in. And yes, calculators can do complex numbers, which is what I'm going to teach you right now. So this is I'm dead serious when I say that why we learn phasors and impedance is because we can use calculators to solve it. And it becomes a very normal job after that, you know? It becomes literally basic secondary school, I dare say, once you know that you can change everything to complex numbers. So let's get into it. So what is a phasor? Well, let me just give you a proper lecture of what phasors is. Phasors is the complex number version of sources. Now, what are the two types of sources we have? We have current source like this, and voltage source, right? So let's say I have a sinusoidal current source. So if I write its function, it will look something like this, correct? Let's just say tan cosine. Yeah, sinusoidal means both sine and cosine, okay? The word sinusoidal is for both sine and cosine. It's just these two wavy shapes. So let's say cosine, let's say 100 t plus 40 degrees, something like that, right? So what you expect this would look like was something like this, some wavy pattern, right? All constant amplitude. If I have, let's say, for example, a sinusoidal voltage source, so V of t, let's say 8 sine 200 t minus 50 degrees. So again, it will look like some wavy pattern, blah blah blah. I'm not being accurate here, but you get what I'm talking about. So the main point is we have entered the realm of alternating currents. So last time, DC currents is just what? If you plot it over time, it just looks like that, a flat straight line. Nothing is changing, not interesting. The more interesting version, the more interesting scenarios will be with alternating currents, which is this. So yes, essentially, phasors is complex version of current sources. So never mind what the hell that means first. We'll get to that. And what about impedance? So impedance is complex number version of resistance. Okay. I will not dive deep into impedance yet because I'll just leave this for the next PTP, I guess. But if you want to feel like you, because I want to get you to understand what is the lecture about. So when you reach impedance, right, just know that it is a complex version of resistance. And we'll talk about this. We'll talk about this for number one, a normal resistor, number two, inductor, and then number three, a capacitor. I don't know if there's more devices, but offhand, these are the ones I can think of. So yes, these have a complex number version for their resistance, and that is called impedance. So I will not touch on impedance in this lesson. I just want to give you an idea of what the hell these terms mean. What the heck is phasor and blah blah blah. And then Professor Domenico is talking about something about encoding the phase or whatever. So which is what I'm gonna elaborate on now, tonight, this evening. So again, this is why I emphasize get your freaking calculator, which I'm gonna teach you how to use tonight. Not exactly, but because the model that I will show you is gonna be totally different from what Booklink sells you. But you get the idea of what you're supposed to press on your calculator. From there, you go and Google or YouTube how to use your calculator for all these operations. Okay? So convert the following into their frequency domain. So what does it mean by frequency domain? It just means convert it to a phasor. Now, when I show you a source, right, an alternating current source, be it a current source or a voltage source, it will always look in the form of something like this. Let's say it looks like this. So it has an amplitude, cosine, omega t plus some phase. So let us identify the parts of this form. So this is called the amplitude. Right? Amplitude is how high the wave is, the maximum height of the wave. Cosine is just cosine, is a trigonometric function, is a wavy function. Omega is what we call the angular frequency. or the radiant frequency. I think they call it the natural frequency, but I think angular frequency is the more common term, or radiant frequency. So this one is in the units of radians per second. Okay? And the last term, this is the Greek letter phi. So this Greek letter phi is denotes the phase. Rather, it's called the phase offset because you offset the graph by some value. Let's say 40 degrees, 30 degrees, whatever. So you can either put this in degrees or radian. And I asked Professor Colin, Professor Lee Hong, he said that you can choose anything. You can choose radian or degrees. You just explicitly tell the grader or the examiner what units you are doing it in. So I'll show you what I mean later. Okay. And another thing to note is this omega, the angular frequency, is given by this formula, 2 pi f. So sometimes they will give you, let's say, 50 hertz. Okay, this frequency is how many cycles it makes within 1 second. So sometimes they'll tell you, oh, a current source has a frequency of 50 hertz, right? This one is in terms of hertz. This one is in terms of radian per second. So when they give you 50 hertz, you cannot put 50 into omega. You cannot just put it straight away like that. You must do 2 pi times 50. Then you can get omega. Okay? So you have to know that. You have to remember this formula. Omega equals to 2 pi f. Okay. So how when I'm given a source, right, a sinusoidal source, how do I write it in the phasor form? So to write it in the phasor form, the most important values to note is number one, the amplitude. And the second piece of information, the phase. Okay, so when I see something like this, and it must be cosine form, it must be cosine here. It must be cosine here. What happens if it's sine? I'll talk about it. So if it's in the form of a cosine omega t plus phi, to write the phasor, it will be like this. A at an angle of phi. Okay, actually, this is a short form. What is this short form for? This is a short form for a e to the I phi, right? We know that this is a complex number in exponential form, right? This is a complex number. But it is so crazy if you have to keep writing a e to the I phi, right? Let's say I have to keep writing 5,000 e to the I times 40, or 3,000 e to the I. I'm already getting tired just writing this, right? So that's why we just short form it to the amplitude and the phase. Okay, so we just write it as a at an angle of phi. Okay, this is just abbreviation. Now you may ask me, how come we don't care about the omega, right? Isn't omega a useful piece of information? Here's the answer why. When I have a circuit, right? Let's say I have a sinusoidal voltage source. All the values, all the other values, right? Which is actually only just current, right? This is a sinusoidal voltage source. The current going through this load, this resistor, is also sinusoidal at the same frequency. So let's say this frequency is 500 radian per second. So the current going through here, right, will be flipping back and forth, up and down at the same frequency, at the same omega equals to 500 radian per second. So if they're the same throughout, right, it's going to be redundant if we just keep saying somewhere, oh, 500 radian per second, 500 radian per second. When throughout the whole circuit, let's say I have more resistors, right? I have more here, I have more here, I have more here, I have more here. Everything, all the currents are going to go back and forth at 500 radian per second. So what's the use? I keep mentioning there are 500 radian per second. It's like I put up a sign and says, "Dear humans, please do not smoke here." I mean, who else can smoke? It's only humans, right? So just no need to explicitly say the angular frequency. Everything will be in 500 radian per second if I hook it up to a source that is flipping 500 radian per second. Okay? So that's why we just ignore the angular frequency. Okay. So let us try this question. Write down the phasor of this voltage source. So you see, make sure that this is cosine, which it is. And now to write the phasor form of this source, you just copy down the amplitude, 170, and then put it at an angle of this. So here, you must include the negative, right? You must include this negative, not just the 40. So it is 170 at an angle of 40 degrees. Now, this is what I mean. Professor Li Hong says that you can put this phase either in radians or degrees, as long as you explicitly write the units. This one. So let's say I hate degrees, right? Say, I don't know, you just don't like degrees, you just like to keep it in radians. So what you do is you change it to radians, so which is negative 40 over 180 pi, and then you must explicitly write radians. It's okay, you can leave it as radians, provided you just tell them, hey, I use it in radians, okay? But for everyone to agree, let's just stick to degrees, okay? So again, I'm gonna recap. You look at the amplitude, you look at the phase, you just copy it down like that. Okay? So can you tell me in the chat how to write the phasor of question B? This is not part of the tutorial, right? In tutorial 6, there is a similar question. There's a similar, they ask you to write the phasor of different sources. So it's similar, if that answers you, Samuel. I just want to provide you more exposure. So can anyone tell me how to do question B? It's just similar to question A. You take the amplitude, you take the phase. So what's the answer? 300 at an angle of negative 50. Is that correct? Yes, it is. Okay. So again, this is the amplitude. This is the phase. So you just copy down the amplitude at an angle of negative 50 degrees. Just like that. Okay. Now let's go to this one. So this case, there is a sign. What happens when you see a sign? You must force it to become cosine. So to force it to become cosine, first, let us change it to cosine. So 10. To change sine to cosine, I write cosine. I copy down the inside. So 1000 t plus 20 degrees. Now, to change it to cosine, I need to minus 90 degrees. This is the important trick, okay? Whenever you are given a function which has sine in it, to change it to cosine, you subtract 90 degrees from the inside. So inside you copy down minus 90. Okay, that's the one of the key takeaway messages. Next, so 20 minus 90 is negative 70. So now how to write the phasor? Tell me in the chat. So what is the phasor of this? After I already changed it to cosine, what is the phasor? Anyone tell me? Tell me. Vishnu? Oran? Ain? Sherman? Samuel? 70, 10 at minus 70. Yes, you're correct. So this is 10, right? I copy down the 10 at an angle of negative 70. Just like that. See? You're starting to feel that phasors is getting easy, right? Hey, why is this? Hey, it cannot be too easy, right? I just copy down the amplitude and copy down the phasor. Oh, it is that easy, okay? So I think you're getting more used to it. Now, let's go to a more difficult question. What about something like this? I have two sources. One is like this is one source, and another source, I combine it like that. How to do this? Now, let me teach you how to use your calculator. So let me make sure how to share this. Okay. So first, let us change these individual sources into phasors. So this one will be 5 at an angle of 36.87 plus 10 at an angle of negative 53.13. Okay, agreed? I think everybody agrees on this. So this is one phasor, this is another phasor. We want to combine them together. How? This is where our calculators will come be helpful to us. So let me just find my calculator here. Okay. So our question is this: 5 at an angle of 36.87 plus 10 at an angle of negative 53.13. So to do this, let us key this into our calculator. So this is 5 at an angle of, so you see this calculator is helpful. They already give me this phasor angle. So I'm going to click this. Then I key in 36.87. Oh yeah, make sure your calculator is in degrees. You see, right now it's in degrees, right? I can change this to radian, but I'm going to keep it to degrees. Okay. Plus 10 at an angle of negative 53.13. Okay. If I get the answer, it gives me in rectangular form, right? Rectangular form of complex number means a plus bi, but I don't want this. I want to keep it in phasor form. So I'm going to keep the answer. So control answer, and then I'm going to change it to polar form. Okay. The phasor is the polar form. So let us find the polar form. So I'm going to go to this number. I'm going to change this to complex number tools. Complex number tools. I don't know why I cannot change it. Huh. I'm not sure why I cannot get the polar angle. That's strange. Hold up, hold up. Okay, wait. Let me restart my calculator. It's funny, I just now it was working. Sorry for the technical difficulties. I don't know what's wrong. So let me try again. So 5 at an angle of 36.87 plus 10 at an angle of negative 53.13. Okay, enter. I should get this answer. Control answer. I want to change this answer into angular form, into phasor form. So I hope I can do that. I don't know what's wrong just now. Tools, algebra. Sorry, not algebra. Complex number 2. I don't know why. Just now it was glitching. So, oh wait. I don't know what's wrong. Control answer. Convert to polar. Sorry. So when I convert this to polar, ta-da! So you see this phasor, right? Okay, I'm gonna recap again. Okay, sorry for the technical disruptions. I'm really sorry. That's my bad. Okay, so let me start again. At first, I'm given this plus this. So I change each of them to their phasors. Everybody knows how to do this. Once I change them to the phasors, I can punch this into my calculator. So I punch it into my calculator, but the answer was in rectangular form. So I will change this to polar form. Okay, I change it to polar form. And then when I press enter, I will get this. So my answer will be 11.18 at an angle of negative 26.56 degrees. So let's check the answer. Yes, it's correct. This is the answer. Okay. So yes, you have to be familiar with how to use your calculator to do this, to do all these complex number calculation. Okay, so go explore whether or not your calculators can do phasors or polar form or rectangular forms, so on and so on. If not, right, if you cannot do this phasor form, then you have to brutally change this to like 5e to the I 36.87, and then you have to brutally change this on to 10e to the I negative 53.13. Then you add these two together and change it into polar form. So if you change it into polar form, right, I think the answer they'll show you is this 11.18 e to the I negative 26.56. Then what you would do is you just read off the values. So this one is this one. Then this one is this one, is your phase. Okay? I hope that's simple enough. So go ahead, explore how your calculator works for complex numbers, and all should be good actually. Now, once we know how to change the source to complex numbers, which is phasors, we have to change it back. So phasors back to complex numbers. So essentially it's the reverse. Let's look at this. So for normal stuff, right, the things that we know, we denote it with small letters, right? Lowercase letters. See, lowercase v, lowercase I. For phasors, we denote it with capital letter. So the phasor of a voltage source is capital V. Phasor of a current source is capital I. So we want to convert this back to the sinusoidal functions. So this is the amplitude. I copy it down. I copy it in the front. And then remember, it's always cosine. So cosine. So they didn't tell us what the angular frequency is. Don't worry, just put omega t plus 26. Right? This 26 comes from here. So amplitude in the front, 26 inside. And then omega t, just leave it as that, omega t. Okay, simple enough. Next, let's go to this. This one, another complex number calculation. So let us key this into our calculator. So 10 at an angle of 30 plus 25 at an angle of 60. Okay, I enter this. I don't like rectangular form, so I take the answer and then I change it to convert to polar. Okay, convert to polar. So this is my answer. I copy it down. Sorry. So I get an answer of 34.03 at an angle of 51.55. But this is not my final answer, right? Because I want to convert it back to the time domain. So it should be a function of time. So copy the amplitude, cosine, omega t, plus the phase, 51.55 degrees. And that's your answer, right? Let me check. Yes. Now, last question. The phasor of 60 plus 30J. Oh yeah, I forgot to tell you. Right now, right, in the how you use complex numbers, remember we say I is equal to square root of -1, but in circuits, right, we don't want to use I. We will instead use J for the square root of -1. Why? Because I looks like current, right? So you will have to use J. We will get used to using J. But in my calculator, it will show up as I, okay? So I'm sorry that you cannot keep that consistency. But when you write stuff, please use J. So how to do this? Again, use your calculator. So I'm going to go back to my calculator. Let's type it in. 60 plus 30i plus 100 at an angle of 28. So I let the calculator do the computation for me. I don't like to see rectangular form, so I change it to phasor. So this is convert to polar. Enter. That should be my answer. So let me just get my pen out. I will have 167.069 at an angle of 27.4 degrees. So again, we want to change it to time domain. So express it as a function of time. 167.07 cosine at an angle of omega t with a phase of 27.4 degrees. That's how you do it. Okay, so yeah, that's it. All the answers are correct. If you want to try this yourself, you can go. I think I'll upload this recording and you can pause it first, and then after that you try to do it yourself, and then you can just play the video to check to see if your answer is right. Yeah. So please get comfortable with using your calculator to do computation for you. I know later in tutorial 7, right, there is one tutorial teaching you the basics of complex numbers. Now, let me tell you this, whether or not you can do complex numbers, right, because in JC and IB, I'm not sure in Poly, we already learned complex numbers. Some of you have already learned complex numbers, and you can be the master of it before anyone cares. But I tell you this, of course, if I give you the chance to do it using calculator, right, and you doing it manually, what would you choose? Of course, you'll be letting the calculator do it for you. It's like asking, hey, whether or not you should bring a gun to a knife fight. Of course, you should take the gun. Don't let yourself get killed, right? If you do all this manually, right, all the, you have to change rectangular to first polar, then you add them together manually, and then do all those crazy nonsense. You'll be stuck in the exam hall and people will leave the hall and you will be there crying while they will be smiling at you. Yeah. So be the one laughing, okay? Don't be the one crying. I guess that's it. I don't want to touch on impedance yet. Yeah, I guess that's it. So I will stop the recording, I guess.